Okay, so in case you didn't catch that, I forgot to start the recorder on the first segment here today, but the second one I did, and this one is being recorded, and I did find out what was going on with my recorder the last time. So hopefully there'll be recorded class sessions going up on the YouTube channel later today. If that all works out, I'll send everybody a link to the YouTube channel. The YouTube channel that you have was sent out by Bob, and is the Dropbox where all the slides are, that was sent to you by Bob, and version 5 is the same one that I've got going right now. So anything before now, if you need to look at the slides again, look at the earlier parts of Bob's class there. Anyway, radio wave characteristics. And this is Technician 3. This is the third sub-element. So you'll notice we're bouncing back and forth with the sub-elements, but that's the way Dan's book is set up. So, all right, amateur radio operation involves the transmission of information by generation and reception of radio waves. So everybody, I mean, people here probably already understand this. You got a radio over here and radio over here, and the way you reach between them is by transmitting waves. One of them transmits, the other receives them, and then they have to be processed once they're once receiving radio collects them on the antenna. They have to go through certain processing. Radio waves are called electromagnetic waves. They are an electric field and a magnetic field, and the E and H are at right angles. On the other program, the program that Bob used to write this, to write the course, this actually shows some animation going on, right? Yeah. So, but you'll see that the electromagnetic, or the E field, the magnetic field is the blue, the E field is the pink there, and they are at right angles to one another, and they intersect at the 0 point, at the 0 reference. What are the two components of a radio wave? Electric and magnetic fields. What is the relationship between the electric and magnetic fields of an electromagnetic wave? Delta, they are at right angles. So we've got Alpha, Bravo, Charlie, and Delta. Frequency, wavelength, and electromagnetic spectrum. The frequency is a number of complete cycles per second. Okay? Unit is hertz, and capital H with a lowercase z is how hertz is represented. Wavelength is the distance a wave travels during one complete cycle. So from the time that the signal first leaves one antenna and it makes one complete cycle, how far does that get? And that's what we're looking at. Represented by the Greek symbol lambda, which is an upside down Y, used to represent wavelength, usually in meters or feet. You will almost always see it in meters. If you see it in feet, it's because somebody with an English accent has converted it. With an American accent, I'll put it that way. Speed of light is 300 million meters per second, and that's a rounded figure. It's actually like 299, 897 or something like that. But we round it to 300 meters because it just makes things a little easier to plug it into your calculator. C is used to represent the speed of light. That's an uppercase C. Radio waves travel at the speed of light in free space. So that free space thing, again, coming back to tell us that your calculations will not be absolute. They're going to be off a tiny bit, but the test is written so that You're not going to have two close answers. And if they are, be sure you look, if you see two close answers, be sure you look at the unit of measure. If it's because almost certain that one of them is going to say kilohertz and one of them is going to say megahertz. Okay, but only one of them is right. Radio waves travel at the speed of light in free space, slower in other mediums. So there's charts running around where you can get what the speed of the signal is inside your coax based on what type of dielectric you have. Air dielectric is going to be higher than the foam core dielectric. Okay, so increasing energy, increasing wavelength. You can see that they are inverse to one another. So as the frequency goes up, the energy increases. But as the frequency goes down, the wavelength increases. And we're really only looking at, well, you've got over here, let's see, at the bottom, you've got a chart there that says vacuum CBA. This one tiny little spectrum in the middle is light that you can actually see. And then when you get up here over on the right-hand side, you'll see radio waves. So that starts to get into the spectrum that we're really most interested in. And remember what I said, from the time it leaves the antenna until it makes a full 360-degree cycle, that is your wavelength. So if whatever your reference is, now in the Navy, when we teach it, the reference is starting at the 0 reference mark, which is all the way over at the left end at the bottom. And then it goes up, and then it crosses back down, and then comes back and meets it coming back up, and that's one full cycle. This makes it a little easier for some folks to understand because you're going from peak to peak rather than somewhere in the middle to somewhere in the middle. So it makes it a lot easier for some folks to understand. Calculating wavelength, speed of light divided by the frequency. So if you know the frequency and you're trying to figure out the wavelength, you just divide 300 million by the frequency. And you want the frequency to be in megahertz. Hertz. But when you take it to 300, you have to do the same thing to both sides of the equation. So when you go to 300, you're going to be in megahertz at that point. Simplify by dividing by 10 to the 6th. So frequency in megahertz is equal to 300 divided by the wavelength in meters. Lower the frequency, the longer the wavelength, higher the frequency, shorter the wavelength. And this will come into play when you're building your antenna. Because as you're building your antenna, if your frequency is too high, it tells you you've probably already cut off too much. If your frequency is too low, you need to trim a little bit. And based on the frequency, you can determine how much you need to cut off. There's actually a formula that I found somewhere that's a little more accurate. But higher frequencies, when you start cutting, you want to cut smaller portions because cutting off a 1/4 inch can make a pretty big difference, cutting off a 1/2 inch. Lower frequencies, you have to cut off more in order to make a difference. Okay, so wavelength is equal to 300 divided by, and all of your answers to these on the test will be in the amateur bands. They're not going to ask you a question where the answer is going to fall outside of the amateur bands. So that's one of the things you can use to help you out on the test. If you know what the band limits are, you know where the you'll know if the answer is in the band or not. And if it's not, then you might want to look for another answer. But your wavelength is equal to 300 divided by the frequency in megahertz. So when you look at this, you're going to be looking at 300 divided by 7.150, and it gives you 41.95 meters, which is in the 40 meter band. To go the other way, if you have the wavelength, but you want to figure out what the frequency is, frequency will be equal to 300 divided by the wavelength in meters, and it'll give you the answer. If you're looking at 300, then it's going to give you the answer in megahertz. If you're looking at 300 million, it'll give you the answer in hertz. So 15 megahertz, that's a little bit above the band, but that's what they're trying to show you right there is your frequency. Yep. 15 meters. Sometimes I get irritated that I'm not doing more time on my radio because now I can't remember the top end of the 20 meter. Okay, so what is the velocity of a radio wave traveling through free space? Speed of light, alpha, 300 meters per second, 300 million meters per second. What is the approximate velocity of a radio wave in free space? Answer B, 300 million meters per second. What is the formula for converting frequency to approximate wavelength in meters? We're going to, okay, so we have the frequency, and we want to find the wavelength in meters. And Carl says C, wavelength in meters equals frequency in megahertz divided by 300. Other way around. So it's delta. Wavelength in meters equals 300 divided by frequency in megahertz, because we're using 300 instead of 300 million. Okay. What is the relationship between wavelength and frequency? How do they react to one another? Bentley? Bravo, wavelength gets shorter as the frequency increase. That is a fact. Let's see. All right. Radio frequency. Let's see. A radio frequency signal of any frequency and wavelength both use one. Oh, what is radio frequency? It's a radio signal of any frequency and wavelength, both used when referring to a radio signal. We use approximate wavelength to identify the amateur radio bands. So when you look at your chart and you're looking at the thing on there that says the 40 meter band is 7 point something, okay, and you start doing all the math and you find out, well, actually that's 40.02. Okay, so they don't go that drastically. It's close. They try to keep it simple. So we use approximate wavelength to identify the amateur radio bands. The 2 meter amateur radio band spans 144 to 148. And by the way, I meant to bring my whiteboard with me so I could write this on there so everybody could get it. But if you're looking at radios, when you're finished with this class and you take your test and you download your license and you're ready to transmit, you've actually got a fairly wide selection of frequencies that you can go to. But the most common bands that you're going to have access to will be the 2 meter band and a 70 centimeter band. So when you're looking at radios on, say, Amazon, for instance, be sure you check for those frequencies. Okay, because some of those on there are going to be set up for different regions where that may not have the width of the frequency allotment that you guys will have. So for the 2-meter band, you're going to be looking at 144 to 148 and I'll go over the other one in a moment. A frequency of 148 megahertz would have a wavelength of 2.03 meters. Oh my God, and they call it the 2-meter band. Okay, so that's why they do that. 2 meters to keep people from panicking. I'm not much different from a lot of hams in the fact that I tend to be a little exact. My wife has a hard time with that because she's very generalized and I'm very exact. So anyway, the entire range of radio frequencies is split into sub-ranges. Before we go into that, the other band that you will have access to besides the 2-meter band will be the 70 centimeter band. And U.S. allotment is 420 to 450, I believe. Make sure before I send you looking for the wrong thing. Yeah, 70 centimeters is 420 to 450. Now there's further things that you will want to look at in there and you'll get some hams that'll want to say, hey, you're not supposed to be here. This is digital only. So to avoid that, you would look a little further beyond what you're allotted to what that allotment is divided up into. And that's really all gentleman's arrangement, but most people stick to it. The entire range of radio frequencies is split into sub-ranges. So we have the medium frequency range, the high frequency range, or HF, which tends to be the meat of what most people do in amateur radio is on HF. Then you have the very high frequency range, VHF, which is what your 1.25 meter and 2 meter is, and 6 meters is in that range too. Ultra high frequency would be above 300, well, from 300 to 3,000. So those are the bands. There's a chart, and this is available on the ARRL website. You can pull their chart and print it out or just save it to your device or whatever. But, and there gives you the exact range there. So your medium frequency range is from 300 kilohertz to 3 megahertz. And HF, like I say, tends to be the meat of what most hams do. So it's 3 megahertz to 30 megahertz. 28 megahertz is the 10 meter band. So VHF 30 megahertz to 300 megahertz, and then UHF 300 megahertz up to 3000 megahertz. In addition to frequency, which of the following is used to identify amateur radio bands? Alpha, the approximate wavelength in meters. And you'll see there's the 160. I think there's 2 medium frequency or low frequency bands down below that, but they really don't get much use because the antennas take up a lot of space. But anyway, those are the most common bands are 80 through, well, from 80 up on that list right there. 160, like I say, doesn't get used a lot because your antenna has to be 80 meters long. Anybody who can tell me what 80 meters is in feet? Pretty close. Let's see. 3, 2, 8. 3.28 times 160. Yeah, 262 feet. That's a pretty big antenna. Most people don't have room for something like that. For antennas should be usually a half wavelength, but you can make them a quarter wavelength. It just requires extra work. Okay, so what frequency range is referred to as HF, high frequency? Charlie. Yeah, 3 to 30 megahertz. Bravo is VHF. That's your, yeah, that's where your 2 meter band, let's see, 1.25 meter band, 2 meter band, and 6 meter band are. Okay, what frequency range is referred to as VHF? Remember to look at the unit of measure. Bravo. Bravo. What frequency range is referred to as the UHF frequency range? Delta, 300 to 3000. Let's see. What does the abbreviation RF mean? Alpha. Radio frequency signals of all types. It seems like it's a lot shorter answer than earlier. Takeaways. Radio waves consist of electric and magnetic fields. Electric and magnetic fields are orthogonal. What does orthogonal mean again? Right angles? Oh, yeah, because they're at a right angles to one another. Wavelength and speed of light. You want to remember this. If you remember one of them, and if you remember the formula in one way, and you're handy with algebra, then you can come up with everything else, because you just apply the rules of algebra to bring it differently. You know, put it in a different format so you can solve for a different variable. C is always equal to 300 million meters per second, and if you use 300 instead of 300 million, remember your answer is going to be in megahertz. Wavelength is in meters. So if you use, yeah, that's actually what I just said. Wavelength decreases as frequency increases. Wavelength is used to represent amateur radio bands. So you've got HF for 3 to 30, VHF 30 to 300, and UHF 300 to 3000, all in megahertz. And RF refers to any radio frequency or radio frequency of any frequency. Okay.